today with the reactors problem, where we've got some reaction going on. Ammonia has been our favorite example process, so why not start there, because we're familiar with it. A gas mixture of hydrogen and nitrogen. So this would be typical of a problem you would see on a homework problem or an exam. In the real workplace, it might be a little different. You'd have to pose this problem and come up with it and write it down. But so a gas mixture of hydrogen and nitrogen is fed to a reactor where they react to form ammonia, NH3. The nitrogen flow rate into the reactor is 150 gram moles per hour. And the hydrogen is fed as a ratio of 4 gram moles hydrogen per gram mole nitrogen. And the balanced chemical equation is N2 plus 3H2 goes to 2NH3. Of the nitrogen fed to the reactor, 70% is consumed by the reaction. The reactor operates at steady state. What is the flow rate in gram moles per hour of nitrogen, hydrogen, and ammonia in the reactor outlet? Let's start with Murphy's steps. Step 1, draw a flow diagram. So let's see, so this is a reactor material balance example. Step 1, draw a diagram. Step 2, define a system. Let's not go too fast here. Make a diagram. Reactor. Robinson, how many streams in? 2. What are the 2 streams? Nitrogen and hydrogen. What's the output stream? And what?
Hydrogen
and nitrogen and nitrogen. Great. What's the system? Yeah, this step seems dumb right now, but it's really important later when we won't think this. The system's the reactor. There's our diagram. The system is the reactor. Great. Let's step 3. Any questions about this? Yeah.
When it looks at a gas mixture, is it okay to assume that they're 2 separate streams?
For the input? Yeah, let's see. So the input could be 1 stream with hydrogen and nitrogen, or it could be 2 streams, 1 hydrogen and 1 nitrogen. It's not too explicit about that. It says, oh, you're right, gas mixture. It is explicit. Gas mixture of hydrogen and nitrogen. So we could draw this as 2, we could draw this as 1. Either way is fine. Yeah, you get, at some point you do get a little bit of liberty to what way to think this. It's definitely 1, it tells you mixture, so it's 1 stream going in.
If they were mixed, how would that work with the 2 different flow rates they give us?
So we could do it that way. Hydrogen and nitrogen in 1 stream. 2 different flow rates. Well, they give you the nitrogen flow rate, so they're giving you not the total, but they're giving you part of this. So another way we could do it is we could write, we could show that nitrogen coming in and the hydrogen coming in to a mixer, and then have the mixture of nitrogen and hydrogen going out to a reactor. Now we have 2 different systems, so we could do a system of the mixer, we could do another system of the reactor. The mixer is fairly boring and straightforward because these flow rates are basically the same as what goes in, but we could do this if we wanted to get exhaustive about it. Yeah. So there's a little bit of choice in some of these. There's a lot of choice in how you do the problem solving. Any other questions about the diagram of the system? So essentially, if we drew it like this, our system here is like drawing a box like this, including the mixer and the reactor. And then if we do that, then we draw this, with the hydrogen here. Let's see, step 3, choose components and define stream variables. What do do you think? What should we use for components? We could do atoms, molecules, or composites. What's going to be convenient here? Atoms, molecules. Again, the answer is, well, composites doesn't really make sense here. Atoms or molecules, either one will work. One will be a little more math and a little more bookkeeping than the other. Sounded like most people said molecules. I think that's what I would choose also. So let's go with molecules for that. So then stream variables. Again, you can label these whatever you want. On Monday we did F for flow rates and we did W for mass fractions. No, we're going to be working on mass or moles. That's step 4 actually, but for units, which also means we have to choose between mass or moles. What are we going to choose, mass or moles? That'll help us with our stream variables. Moles. Why? Okay, they gave us moles, but I could have given you mass. And it still would have been better to go with moles. Why? Because we're given stoichiometry because it's a reaction. A lot of times when there's a reaction with no stoichiometry, this is moles. 1 mole of nitrogen plus 3 mole of hydrogen. We don't really, the mass we'd have to do more calculations. So moles is a good choice here. Okay, so stream variables. We've got nitrogen going in. Let's call that N in. Hydrogen going in. Let's call that H in. Coming out, I've got ammonia going out, hydrogen going out, and nitrogen going out. I'm making a choice here. I could have done flow rates and mole fractions. Why do I know to do this? Because counting moles is good because I've got chemical reactions. I know moles going in. I might know moles converted that would help me do moles. So working in whole moles makes sense to me here. If you did fractions, it would still work out. You're just going to have more variables and more math. So if you go down the path and you're doing lots of variables and lots of math, you might stop and go, wait a minute, should I have made a better choice? Basis. What's our basis?
The nitrogen flow rate.
The nitrogen flow rate into the reactor is 150 gram moles per hour. Sounds like a good enough basis to me. We're given it. Nitrogen flow rate, what's the variable there? N. 150 gram moles per hour. Great. Step 6, system variables. Again, you can choose different things for the basis. If you chose the basis of 1 mole per hour of ammonia coming out, you could do that and then rescale later. Again, still multiple choices. Step 6, system variables for generation, consumption, and accumulation. We didn't do this last time because we didn't have it. We did, but we didn't just zero them all out. So is there generation, consumption, or accumulation? Yes, I'll have generation. So what's generated? Ammonia. So let's have ammonia generated. What's consumed? Nitrogen consumed and hydrogen consumed. A lot of times I'll put this on my diagram too. So in the reactor I've got ammonia generated, nitrogen consumed, and hydrogen consumed. Okay. If the system is not at steady state, define accumulation. Is it at steady state?
Yes.
Okay, they told us that. Great. Step 7 is stream and system specifications. You should do those yourself. Write out some equations with your partner. What specifications do you see the problem, and can you write it in terms of all these variables now that we've written it down?
Right. But I did since there's 4 gram moles of H2 going in for every M2, I believe I multiplied that by 50.
Well, okay, there's 4 gram moles H2 per gram mole N2. Okay, so you use that, you calculate, okay, so let's write that, let's start with that as an equation based on the variables. Did you do, can we write an equation with these purple variables here? 4 gram moles of hydrogen per gram mole of nitrogen. What's the equation? Hn equals 4 Na. So this is, and what it, so this is these are specifications. And these, is that a system specification or a stream specification? Stream. That's a stream specification. Let's talk about the composition of, this is where our diagram is a little funny. It's actually one mixture stream going in. It's talking about that composition. Great. Okay, then from that, you're right, Ebony. So then you went ahead, and we know N, so you got 4 times 150 g-mole per hour. So you got 600 g-moles per hour of hydrogen N. Super. RJ and Adam, do you guys have another spec?
N equals the out plus consume.
In equals the out plus consume. Is that a specification of a stream or a specification of a system performance? That's a trick question. So you're jumping ahead again. You're doing Jack's trick from Monday. I'm jumping right ahead. That is a material balance. You're balancing everything in and out and what's getting consumed. That's going to be step 8. So hold off on that one. How about any other specifications about streams? Do you know anything about the output stream? It's the input stream? Yeah?
0.3 equals N out.
0.3 times N in equals N out. Where did you get that from?
Because 70% is of the nitrogen goes through the reaction. So that's 30% is about the
70% of the nitrogen fed to the reaction is consumed. So this is what kind of specification? Let's see. This is a stream specification. This is this specification of streams or the system? This is the system. So this is telling you how well that reactor is operating. Here's our system spec. So 70% is consumed by the reaction. And you did some quick math in your head, so that means there's 30% left that comes out, right? That's how you got the 30%. Okay, so I could also write this with the 70%, just based on what's written. What's your name? Anish, yes.
N consumed is 0.7 times N in.
N consumed is 0.7 times N in. So we have this system variable of how much is consumed in the reactor, so we can use that variable. What's consumed is 70% of what goes in. All right, step 8, material balances. RJ, any material balance on some species. Or Adam, you were the one who gave it to me, right?
So either H or M in equals the out plus consume.
Equals H out plus H consumed. The hydrogen that goes in is either comes out or gets consumed. Either H or N. How about N? Let's do both. N in equals N out plus N consumed. All right, this is good. You're doing it intuitively. You just put these together. You can also go back to our big master equation. In minus out plus generation minus consumption equals accumulation. Accumulation is 0 because steady state. Generation is 0 for these because no reactions generating this. We have in and out, one of each. Okay. Okay, hydrogen, nitrogen. How about ammonia? What's the material balance on ammonia? In. What's in for ammonia? Everybody? 0. Out. A out, generation, plus A gen, consumption,
0.
0, accumulation,
0.
0. So minus A out plus A gen equals 0, or A out equals A gen. Anish?
I have a quick question about, for number 7, do we have to say like 2 times N consumed is A gen? Like, do we have to use that?
Ah, shoot, I did erase that. Yeah, step 7 says, step 6, define system variables for generation and consumption. Yeah, there's tricks here. Actually, there's like 2 more pages to this in the book with a whole bunch of tips. It's worth reading all those tips for all the different kinds of problems. Let's see, but the big one is actually written here. If there are chemical reactions of known stoichiometry, write equations using system variables which relate generation of products to consumption of reactants. So can we write equations between N, so we know N2 plus 3H2 goes to 2NH3. Anish, can you give me a couple equations?
A gen equals 2 times N consumed.
A gen equals 2 times N consumed. 2 ammonia is generated for every nitrogen consumed. Yeah, give me another equation.
And then 3 A gen equals 2 times H consumed.
3 times the ammonia generated is 2 times H consumed. Let's see, because I have 3 times this, got 2 of those, is 2 times that, because I've got 3 of those. Does people agree with that? I'm a little confused, but that looks right to me. Yeah, any more equations? I don't think so. We'll talk about this on Friday. How many equations can you write? The answer is number of species minus 1. You can write 2 equations. There's different equations we can write here, just like these 2 are the same equation. I might have written N consumed equals 3N consumed equals H consumed. Because I've got 3 times as much hydrogen as N being chewed up by this reaction. It turns out this is redundant with the 2 of these, right? Actually, I could combine, I could get rid of the A gen here and get this equation out too. So, or that one, or that one. Okay, that's on.
So this is all under step 6, right?
This was under step 6, yeah. This is under system variables. All right. Okay, so you go through all these steps. You're going to have a bunch of equations written down on the paper in different places. And the basis step, this one, material balances, we got those. System specs, we got HN. Okay, so what I would do is fill out your diagram as you go. So N in is 150 millimoles per hour. HN we figured out over here, right? So we have 600 millimoles per hour. Let's see, N consumed equals 0.7 N in. So N in is 150, so 0.7 is 150 gram moles per hour is what?
105.
105 gram moles per hour. So what is that? N, that's N consumed. It's 105. Erase this for now. 105 gram moles per hour. Once I've got that, then this stuff plugs in from N consumed. Twice that is the A gen, so that's going to be 210 gram moles per hour. And we're doing step 9 now, which is solve, right? So 9. Start plugging things together. H consumed, how can I get H consumed? H in minus H out, but I don't know H out yet. 3N consumed is H consumed, so N consumed is 105, so I'm going to get 315 millimoles per hour consumed there. Now, how do I get the outs? That's all over there, right? Material balances, the outs, the ins minus the consumed. So A out is the same as A consumed, 210 G mole per hour. H out from my material balance, H in is 600 minus the H consumed is 315, so the H out is 285 millimoles per hour. And the N out, N in is 150, and consumed is 105, so the N out is like 45 millimoles per hour. Step 10, are we done? We're not done, there's a step 10, what's step 10? Check. So one good way to check is to make a stream table. So in this case, we could do nitrogen, hydrogen, and ammonia. We could do stuff coming in, generated or consumed. We could do stuff going out. We put this whole table together and make sure it all makes sense. So N in is 150 millimoles per hour. H2 in is 600. The same. Ammonia, there's none coming in. Generated or consumed. Nitrogen has 105 minus 105. Consumed, I'll put a minus there. G moles per hour. Hydrogen, 315. Ammonia, 210, and then the output, 45, 285, 210 G moles per hour. So I can make a table like this, and then I can go through each of these specs, make sure, did I get the 4:1 ratio, did I get the 3:1 H2 moles? You can go through each of these. So this would be like a summary table. It's also a really nice way to present results. You can also do that in Excel. The other way you can check, how else can you check? So one of the best ways to check is to convert this to mass. So if you convert each of those to mass, the total mass that goes in has to be the total mass that comes out. So I would do total mass in equals total mass out. If that doesn't work, either you made a mistake changing it to mass or you made a mistake somewhere else. So I would look for different ways of looking at your numbers at the end to check. Any questions about that? Next one I'm going to look at is separation with accumulation air drying. What kind of process mode is this in? Remember the modes? Batch and continuous. Batch. Why do we say batch?
It says that the tank is supposed to be stopped.
We're hearing about things starting and stopping. That sounds like a batch. Why are we unsure?
Because there's a flow rate.
Stuff's flowing through. This is a semi-batch, semi-continuous. We do a batch of alumina. The stuff gets, then we continuously flow the wet air through, accumulates lots of water, and eventually the alumina's full. We gotta stop and pull it out, replenish it, or dry it out, or something like that. So this is a semi-batch process. So what's on the diagram? So this is our dryer. What goes in?
Wet air.
Moist air, humid air. Comes out.
Drier air.
Drier air. Same Okay, so some of it comes out, the rest of it stays here. That's accumulation. So we're going to accumulate water. So I just jumped to the system variables part. So I've got water accumulating here. So I've got alumina, pellets, and then accumulating water. All right, and then sometimes with batch we can do that cartoon format. We have different panes in the cartoon. You have the beginning, it's all dry, and then during the continuous part, stuff's going on until the end. So we could actually draw 3 panes for this where there's no water here, and then we're accumulating water, and then at the end, this is really just that middle pane where we're accumulating water in a phase. Okay, there's a diagram. Step 2. Step 2.
Identify the system.
System, what's the system?
The dryer.
Separator, dry separator.
A dryer, which is a separator. Step 3. Step 3. Components. What should we use for components? Atoms? Molecules? Molecules, okay. So I haven't done any with atoms. There are some in the book. Do some with atoms so you see those. So let's do molecules. Define stream variables. What variables do we have for stuff going in? Well, this is air. This is humid air. Is that sufficient then? Should you say air in? It's just a little tricky. We do that flow rate of the whole thing and have fractions for different things. So we could do like a total. There's different choices. You could do flow rate, and then you could have mass fraction of water and mass fraction of completely dry air. We could also just use the whole component, so all the air in and all the water in, like we did with the last problem. I find that easier because there's just less to carry around, but they actually give you mole percents, not mass percents, so we could go with mole percents, XA and XW. That's not a bad way to do it because they give them to you. So either way is fine. I don't know. I like doing it this way when I can just because it's, I like thinking about whole numbers, but you might like it the other way. What comes out?
Air out.
Air out.
Water out.
And water out. Okay, so this A is completely pure air, dry air. It's actually a mixture too, right? It's nitrogen and oxygen, argon, etc. But we'll treat it as one. That's actually a composite. We're going to treat that as a composite molecules of air. Step 4, units. What units should we use? You can do it in mass if you want. I didn't, so I'm going to change it to moles. Let's do moles. But you can do it in mass if you want. Just have to convert things to. I like the mole percent, so that's handy. And there's another reason why I want to do moles. So we'll get to it in a second. How about the basis? It's a good basis for this problem.
The flow rate in.
Flow rate in. What's flow rate in?
100 cubic feet per minute of the humid air.
Flow rate in is 150 cubic feet per minute. Okay, how's that fit with my variables and my units?
And plus W in is 150.
Okay, so the total flow rate is A in plus W in. So this is A in plus W in. But then feet cubed per minute are not the units we chose. So one thing you can in the unit step change everything into the consistent units. That's what Murphy recommends. I think that's not a bad idea because you get it all into moles and you can't make mistakes with units anymore. So she suggests you go ahead and convert everything right here and then. Okay, but because if we're short of time, we'll just do it as we go here. 150 feet cubed per minute. How do I change this to moles?
Oh, it's 100 cubic feet per minute.
100 cubic feet, thank you. I like that make up your own numbers for the problem. Make sure you state really clearly what numbers you used when you make up your numbers for the homework, so they can make sure they give you the right numbers. Okay, how do I change that into moles? It's volume. It's volume per time. Okay, Paige?
Use ideal gas law.
Ideal gas law. Did they tell you that?
They told us about the information.
They have temperature and pressure.
They give you temperature and pressure. That's a good hint.
It's not gonna be ideal at high temperatures though, so you can just use like boils longer. You can just be like.
It's not going to be ideal at high temperature. Is this high temperature?
Oh, it's Fahrenheit, that was Celsius.
Yeah. This is pretty fine. So I want to, so the temperature's mild, the pressure's mild. That's another hint, ideal gas law. But that's good. Be on alert for non-ideal gases. Next semester in thermo, we spend a lot of time on that. Lots of different non-ideal gas laws. In this class, it's mostly the ideal gas laws, so you usually get away with that. Okay, right. So volume equal. Let's see. So if I change that to what I want to convert it there.
So you're going to do PV equals RT and then find out ratio of volume.
Let's see. PV equals nRT. So if I've got the volume, that's going to be pressure nRT over P. N, I want the moles. N is going to be PV over RT. So here's my V. I want to multiply by P, divided by RT, and that should give me moles per time. We're out of time, so I'm not going to do all of that for you. Let's pretend we get 0.277 pound moles per minute out of that. If you don't believe I can get that, you can ask after class. I will hold off till our stay after class.
In the